Now this is an applied example. Suppose that at another gas station, the daily demand for regular gasoline is normally distributed with a mean of 1,000 gallons and a standard deviation of 100 gallons. So we have a normally distributed random variable with a mean 1,000 and standard deviation 100. The station manager has just opened the station for business and notes that there is exactly 1,100 gallons of regular gasoline in storage. The next delivery is scheduled later today at the close of the business, and the manager would like to know the probability that he will have enough regular gasoline to satisfy today's demands. So he wants to know whether what he has in stock, the 1,100 gallons, is enough or not. Our normal random variable in this case is the demand for gasoline, and it has a mean 1,000 and a standard deviation 100. What we want to find is the probability that the demand is less than the stock, less than 1,100. So we are trying to find the probability that X is less than 1,100. If we draw a graph, we will find that the mean here is 1,000, and what we want to find is the area or the probability that the variable is less than 1,100. It is this red area over here. We need that the first step is always to standardize the so the probability that X is less than 1,100, we want to transform this X into a standardized normal random variable Z. So what do? We have to subtract mu and divide by sigma. And we know that to keep the inequality, if we do this for X, minus mu over sigma, we have to do it on the other side of the inequality too. So it's 1,100 minus mu, which is 1,000, divided by 100, the sigma. So doing that, the X is now called Z. It's a standardized normal variable. And calculating this value over here, we find that it's equal 1. So we want to find the probability that Z is less than 1, the shaded area that we saw on the previous slide, which we can get by splitting again into two parts. From negative infinity up to 0, this is 0.5, plus the probability that Z is between 0 and 1. Go back to the table. From the rows, find 1.0, and from the columns, find 0.00, and the corresponding probability is 0.3413. So adding this to 0.5, the total probability is 0.8413. And this is the area or the probability that we want to find. Let's look at another example here. The scores of a GMAT test are normally distributed with a mean of 494 and standard deviation of 100 points. The GMAT is a test of English and mathematics, and in this case we know that it has the scores have the normal distribution with these mean and standard deviation. The first question is, what is the probability of obtaining a score greater than 700? So we need to find the probability that X is greater than 700. Again, the first step is always to standardize. How do we standardize? We will subtract the mean, 494, and divide by 100, which is the standard deviation. By doing that, X becomes Z, and the 700 minus 494 divided by 100 becomes 2.06. And we want to find the area from 2.06 up to infinity, the Z greater than 2.06. So it's this little shaded area in the tail of the distribution. Again, how do we do this? We do this by knowing that the area from 0 to infinity is 0.5. minus the area from 0 up to 2.06, which we can find from the table to be 0.4803. So doing the subtraction, we find that the probability that we want to find is 0.019 7. So we can say that there is a 1.9% chance that you get a score that is greater than 700. Another question on the same problem. What's the probability of obtaining a score that is 550 or less? Of course, it's very important in such questions to translate from English to statistics. So a score that is 550 or less means the probability that X, the score, is less than or equal 550. Okay. Again, we will have to standardize by subtracting the mean and dividing by the standard deviation. So we obtain this, the probability that Z is less than or equal 0.56. We know that the equality doesn't make any difference in case of continuous distributions. So we just go and draw the curve and shade the area that we want to find, which is less than 0.56. It is this shaded area over here, which can be split into two parts again. From negative infinity up to 0, the area is 0.5, plus the area from 0 to 0.56, which can be found from the table to be 0.2123. So adding those two together, we get 0.7123, which means that there is a 71% chance of obtaining a score less than 550 or less. What is the probability of randomly obtaining a score between 300 and 600 on the GMAT exam? So we want to find the probability that X is greater than 300 and less than 600. We can notice that 300 is a value that is less than the mean, and 600 is a value that's greater than the mean. So when we do the standardization process on both values, 300 becomes negative 1.94. It's a negative value because it's less than the mean, less than 0. And the 600 becomes 1.06, a positive value because it's greater than the mean. So when we draw the curve and put down those values, negative 1.94 and 1.06, so we want to find the shaded area between those two values. Again, this can be split into two parts. The area or the probability that X is between 0 and 1.06, which we can find directly from the table to be 0.3554. And the other part is the area from 0 to negative 1.94. There are no negative values in the table, so we use the symmetry to say that, okay, this will be the same as the area from 0 to 1.94. So take 1.94 to the table and find the corresponding probability. It will be 0.4738. Adding up those two values, we get 0.8292. We are still in the same example of the GMAT scores. Now we want to find the probability of getting a score between 350 and 450. Again, it's the area or the probability between two values, but this time we can notice that the two values are less than the mean. The mean is 494, so both values are to its left or less than the mean. So the probability that X is greater than 350 and smaller than 450, by doing the standardization process, X minus 494 divided by 100, it becomes Z. And 350, doing the standardization, it becomes negative 1.44. 450 becomes negative 0.44. Again, don't forget to draw. We will have two negative values in this case because they're both less than the mean. This is negative 0.44, this is negative 1.44. Can we find this area, or can we find this probability? Yes, we can. We will find the area from 0 to negative 1.44 minus the area from 0 to negative 0.44. So we obtain this area over here. Remember, that there are no negative values in the table. So what we will actually do is we will find the area from 0 to 1.44 minus the area from 0 to 0.44, and by symmetry it will give us exactly the same results. It's 0.4251 minus 0.17, so the final result is 0.2551. We have learned how to use the table in one way, whether we had a standard normal random variable or a random variable that had to be standardized first. In both cases, we reached to the point where we have a value for z. We used it to look it up in the table from the margins and find the corresponding area or probability from the body of the table. Now we want to do the other way around. What if we are given the probability or the area, and we want to find what is the corresponding value of z. So looking at this curve over here, let's say that we know that the probability that z exceeds some value is given by this shaded red area over here. So we are given the area and we need to find za. Can we do this? Yes, we can, using the same tables, but we will use the tables in a reversed way, meaning that we will be given a probability, so we will be looking into the body of the table, and then we will try to find the corresponding value from the margins. The z value, we get it from the margins. We will see how we're going. For example, we want to find the value of z, let's call this za, that has area to its right equal 0.025. This is 2.5% of the total area, 0.025. First, we denote this value here. We call it z 0.025. This means that this is the z value that has area to its right equal 0.025. So can we find this value? In order to use the table, we know that the areas given in the table are from 0 up to a certain point. So we need to subtract. We will use 0.5 minus this shaded area, 0.025. We obtain 0.475. What is 0.475? This is the area from 0 up to a certain value that we need to find or to look up in table 8.5. So if we go back, we go to back to our table, and now we are looking for the value, the z value, that corresponds to an area 0.475. We know that the areas or the probabilities are given in the middle of the table. So this is what we have now. We need to look for 0.475 and then see the corresponding z value. So let's have a look here. This is 0.473, 0.4744, here 0.4750. So what is the corresponding z in this case? First look at the row, because it gives the whole number and the first decimal place. It is 1.9. And then look at the column, which gives the second decimal place. So it is 1.96. This is the z value that has area 0.4750 before it, and consequently it has area 0.025 to its right. So this is the value we are looking for in this case, 1.96. This is how we do the reverse lookup. Another example, if we want to find the value of a standard normal random variable such that the probability that this random variable is greater than this value is 5%, meaning that we want to find the probability, the value of z that has area greater than it or to its right equal 0.05. So it's exactly like the previous example. We want to find this z 0.05. Again, we know that the probabilities or the areas in the table are from 0 up to z, not from z to infinity. So we will do the subtraction, 0.5 minus 0.05. We will obtain 0.45. Take this probability to the body of the table. Try to look for the closest value. And then find from the margins the corresponding z. The corresponding z, you will find it to be, you will not really find 0.45 exactly. You will either find 0.4505 or 0.4495. So you can take either this or that or the average of both values. So it is, the corresponding z is 1.645 or just 1.65 is okay. If we want to find the value of a standard normal random variable such that the probability that the random variable is less than it is 5%, we need to draw this. Let me try to draw again. So it's as if we have, this is our standard normal curve, and we want to find some value that has area 0.05 less than it. This value has to be on the left hand side, and it has to be here, because the area 0.05 less than the value, it means that there is 5% here, and we know that the total area is 1, so it cannot be on the right. If it's on the right, then the area to its left has to be something big, greater than 50%. So we try to find this value z here that has area less than it, or area to its left, 5%. We will use symmetry again to say that the point that has 5% less than it is the same point that has 5% greater than it with a negative sign. So we just found this z.05 to be 1.65, then this one on the left hand side has to be negative 1.65. We have an applied example now. A university is introducing a new MBA program. One of the entrance requirements is that the applicants must score in the top 1% of the GMAT scores. So the university wants to have only the top students, the students who, the top 1% of all students. The GMAT scores are normally distributed with a mean 490 and a standard deviation 61. So these are mu and sigma. The question is, what should the university set the minimum GMAT score for admission? So let's think about it. We need to find the score that has 1% above it, okay? And we will actually need to find it in the standard form and then unstandardize it to get it in terms of the GMAT scores. Let's see how we are going to do this. Let's say that the minimum GMAT score that we want to find, this will be announced by the university that this is the minimum score that you should get in order to be admitted to our university. We will call it A. Okay, so we want to find this A to make sure that only the top 1% are admitted. So if we come to look at the normal curve, we are actually looking for some value that has 0.01 area, this is equivalent to the 1%, to its right. Okay, but first, let's write it in terms of probability. So what we know is that the probability that x is the GMAT score, is the random variable, is greater than a certain value A is 0.01. Let's standardize, because we cannot work with unstandardized values in order to use the table. So standardizing by subtracting 490 and dividing by 61, we will get the probability that Z, because now it's standard, is greater than some value that we will call B. Okay, so from the table we can find this value B. It is the value here that has area to its right equal 0.01. Again, as we did in the previous examples, we know that we need to find the area from 0 to B. So this is 0.5 minus 0.01, so it's equal 0.49. Take this 0.49, go to the body of the table, the middle of the table, and find the corresponding Z. It will turn out to be 2.33. In the row you will find 2.3, and in the column you will find 0.03. Okay, so this is the Z that has 0.01 area to its right or greater than it. Okay, are we done? No, not yet, because this is done in terms of the standard normal. We want now to transfer this into the problem itself. We need to know the GMAT score. What we know is that B is A minus 490 over 61. This is how we did the transformation, how we did the standardization. So now we know that B is 2.33. What we have to do is a cross multiplication, solve for A. You will find A to be 632.13. So this university needs to put in its admission requirements that we will not accept students unless they score 632.13 on the GMAT or more, of course. This guarantees that they get the top 1% of all students who take the GMAT score. One more final example. Translate the words. What do we have? We are looking for a probability. So we use the table like we learned the first way, look in the margins and find something in the middle of the table. Or are we given a probability and we want to find the corresponding value? In this case, looking at the last part of this question, it says of the daily amounts of waste generated per person, 67.72 would be greater than what amount? So we are given a percentage which is equivalent to a probability, which is equivalent to an area, and we want to find the corresponding amount. Remember again that the best way to approach such questions is to draw. So let's look at the solution. We are looking for a value, let's call it A, such that the probability that X is greater than this value is 0.6772. This is 67.72% divided by 100, okay? So we must know that this point A has to be on the left of the mean. Why is it so? Because it has area to its right 0.67. This is greater than half. So if we say that this point is here, how can this area to its right be 0.67? It is not logical. So we need to have a point that has area to its right 0.6772 by having this point to the left of the mean, because we know that this area from 0 till the end is half, and then we will add 0.1772 to get the total area. So the question is, what is this value here? So the probability that X is greater than what is 0.6772. As usual, the first step is to standardize, because we cannot work with unstandardized normal random variables. The standardization brings us to this second step, that the probability that Z is the standardized version of X, is greater than some value B. What is B? It is A minus the mean divided by the standard deviation. So it's A minus 3.58 over 1.04. I will just call it B for now. So we have an area 0.6772 to the right of B. So what is B? We know that the table gives areas from 0 up to a certain value. So we will look from 0 to which value will give us 0.1772. Take the 0.1772 and look it up in the middle of the table, in the body of the table. You will find that the corresponding Z is 0.46. But remember, this value is a positive value because this is what you can get from the table. But you know that our value is on the left side, so it needs to have a negative sign. It is not 0.46, it is negative 0.46 by symmetry. So we have just obtained the correct B. It is negative 0.46. Are we done? Not yet. We have one last step to do, and it is to convert this B in terms of the question, which is A. We know that B is A minus 3.58 over 1.04. Now we have obtained B. It is negative 0.46. Do the cross multiplication to obtain A. It is 3.58 plus negative 0.46 multiplied by 1.04. So it is 3.10. And this is the solution for this problem. And this brings us to the end of this chapter about continuous distributions.